Okay. We solve a few problems on statically determinate structures in the last class, and today we are into statically indeterminate trusses, not trusses, torsional members. Here is a picture of a statically indeterminate member. Okay, if you can see, if you can properly see, there are two fixed boundary conditions here at A and at B. Okay, all right, and then there are two torques that are applying on the structure. One is here 800 Newton meter at C, which is 0.2 meter distant from B, and then we have another torque here at D, which is at 0.3 meter distant from A. Look at it. Okay. Now, as we all do, this we have to solve for it twist. So we have to plot the twist diagram. Okay, deformation diagram. So what we do, first job is to free the body, right? So what we do is we free both the boundary conditions. Let us free it. So we feed both the boundary condition and we put, so since we are freeing boundary conditions, we have to give appropriate forces in the boundary condition. So I gave a TB force here and I give a TA force here. Now this TB, TA, both are unknown to me, right? I don't know either of them. So how many unknowns we have? Therefore, I have two unknowns. One is TA, the other one is 2TB, right? And how many equations we have? Generally, this is a 2D problem, so we should have three unknowns. So summation of FA equal to 0. Can I use it? No, I cannot use it because there is no fx, there is no fx, right? So I cannot use that. Summation of fi equal to 0. Similarly, there is no fy, so 0 equal to 0. Last one is moment equal to 0. So I have just ended up with only one equation, that is moment equal to 0. Right, so summation of all the torques have to go to 0. That's what I have. So I have only one equation and I have two unknowns T and TB, and therefore this is certainly a problem in statically indeterminacy. What is the degree of indeterminacy? The degree of indeterminacy is number of unknowns minus number of equations I have. So it's going to be 2 minus 1, 1. Okay, so I need to find one more equations from my compatibility equations or from my deformations equations, right? And if I get that, then my solution is available with me. Now, before I go to that position, let me write the equations for the equilibrium itself. How do I write the equation of equilibrium? Now, please pay attention here because this is where you will again ask me questions. So pay attention. I have drawn TA and TB, whatever clockwise or anti-clockwise, whatever I want, I've drawn it. No matter, right? Because if the values come out to be positive, then my choice of directions are correct. If the values come out to be negative, then I have to change my assumed directions to the opposite one. All right. Now, when I look from this side, okay, this TB is positive or negative. So it is going inside, right? If I do a thumb rule, this looks like inside. So if I draw the same thing here, okay, if I draw the same thing here, so this TB is towards inside. So this is inside. Now this is at C, right? TC 800 Newton meter is opposite to TB, right? So that has to be positive. If this is negative, TB is negative, then TC has to be positive. So that's on this side. Similarly, D is opposite to this TC, and therefore that goes to the negatives this side, right? So the direction changes, and TA is along the direction of D, so it is also should be along the same direction. All right, clear? So I'll tell again. What I'm doing is I'm choosing a positive or negative based on my right hand thumb rule for one of the torque, right? One of the torques. And based on its clockwise or anti-clockwise orientation, I can put positive or negative for other torques. That's what I'm doing. So for first thing is I am trying to find whether TB is positive or negative. So it seems to be the TB, the torque direction is towards inside the rod, right? So it's going to be something like this in this diagram. Now, based on that, TC is going to be on the opposite direction. So its direction is this way. Similarly, TD is along the direction of TB, so it's going to be that direction. And TA is along the direction of TD, so again it's going to be this direction, right? Clear? Now I can write the equation. If my TB is negative, so this is TB is negative, then C is going to be positive, D is going to be negative, and A is going to be negative, right? Sorry, A is going to be positive. No, A is going to be negative. So it's along the direction of TB, so it's going to be negative. So I put minus TB plus 800 because this is on the positive direction, opposite direction to that. 500 is along the same direction, so minus 500 minus TA because that's also along the same direction. Now total of that is going to be 0. So done. So that's my equilibrium equation. Do not make a mistake here. There are a lot of chances of making mistake here. Don't make that. All right. Now that's my equilibrium equation, and I need one compatibility equation to solve the problem because there are two equations that are necessary to solve this problem. Where do I get a compatibility equation? If I look at the problem carefully, my problem has fixity at B and fixity at A. Therefore, both B and A are not moving. The rest of the section is getting twisted, fine. But at B, there is no twist. At A, there is no twist. It's like a fixed pin. Okay? So no twist. That's my boundary condition. Therefore, rotation at A with respect to B is 0. Similarly, rotation at B with respect to A is 0. Okay, so phi A
Sir,
given B is, yes,
so smart also. Sir, here this rod is fixed at ends A and B, sir. So basically, like ends
yes,
A and B won't rotate with respect to the ground itself, no, sir. So why would we take rotation with respect to B, sir? Like because this A is fixed with respect to wall, sir. So
yes.
so why do we take it like the angle of A with respect to B?
Yeah,
Is it like
because rotations or deformations are given relative to one another, right? I can only find rotation at A if I know rotations at B. Okay, otherwise I won't be able to find it. So I'll assume this guy to be fixed, and then I calculate rotations at C, rotations at D, and finally rotation at A, and then tell that A has 0 rotation with respect to B, right?
okay, sir? I get it, sir.
Is
So
that
so
clear?
so if yes, sir, if A is fixed, then the entire rod will be fixed, no? So the like no part of the rod will rotate, no, sir. Like, just a
Oh,
question, sir.
no, no, no,
Not related to the
no.
question.
I'll just give you a practical example. You have family members in home, right? You take a, you take a big cloth, okay, and then soak it in water. Try to tell your two relatives to hold at the two sides tightly so that those two portions are fixed. Doesn't rotate. Now, somewhere in between, you put your two hands and rotate it, twist it. You will see water will drain down and you will see it's to be twisted. So, although the sides are not twisting, inside it will get twisted, right?
So even
Isn't
for
it?
an axis symmetric thing, it will get twisted, sir. Like
Yes, it will get twisted. Because I'm giving load there, right? Wherever I'm giving a torque, it has to deform that portion. Whether it deforms outside or not doesn't matter. But that portion it has to deform. That portion it has to change its angle. Okay.
okay, sir.
All right. Sometimes you might have seen, I don't know that's a good example or not. If you have a big rod and you want to, wooden stick and you want to break it, and you single-handedly cannot do it, so you ask people to hold on the other sides and try to rotate it from the center so that it breaks. I don't know whether I've seen it or not, but the other one probably it's a good example to do at home. Soak a water, maybe a big, you know, bed sheet or a bed cover you can take and soak it in water because that's going to be long. And try to do that experiment and see whether it happens or not. Okay, so yes, so we need a compatibility equation, and the compatibility equation comes from that deformation at A with respect to B is going to be 0. I have written with respect to B because I have to calculate phi of A with respect to B. Okay, or I have to calculate phi of B with respect to A. I have to calculate either of them and put them equal to 0. Yeah, so now how do you calculate phi of A or phi of B? Very simple, right? We have understood that formula last time itself, that phi of A given B is phi of 1, phi of 2, phi of 3. You have to just add up. So this might be phi of 1, that is my phi of 2, and that's my phi of 3. I have to add all the phi's and calculate the total phi. Now for doing that, I need to find the internal torque acting here, the internal torque acting here, and the internal torque acting in this section, and then add up, right? So the formula is, if you remember, is summation of phi Ti into Li divided by Gi Ji. So Ti Li Gj. Now Gj is constant for the member because it's a single rod. Now TB is going to act at this portion of the member, right? If you take a free body diagram here and if you look at this portion, that's TB. Okay, so phi 1 is going to be minus TB because it's minus, I have given minus TB 0.2, this length is 0.2 by Gj. Similarly, this portion is going to be 800 is my positive, TB is my negative, so it's going to be 800 minus TB, this portion, right? If I take a section here and look from this side, it is 800 positive and TB negative, right? So 800 minus TB into this length from here to here is 1.5, right? This length is 1.5. So 1.5 by Gj plus the rest of the section. Okay. So that you can take a cut here and you can look on the other side. So that will be only 300. 300 minus. Okay. Total is 300, right? Or what? Oh, yeah. So that's going to be your minus 500 plus 800 minus TB. So 300 minus TB into 0.3 equal to 0. So with this, you can solve for TB. Because this is phi 1, phi 2, phi 3. That total should be equal to 0, phi AB. And that solves your problem with TB equal to 645 Newton. Once you know this, you can put this into the equilibrium equation and solve for TA. Okay, so you can put that and solve for TA. Now that solves my problem. But as an engineer, you have to draw, as I said earlier, you have to draw torque diagrams, you have to draw twist diagrams. So here is how you have to draw torque and twist diagram. So this is the rod that was given to us, and that was my forces, right? This is my TB, which is now known. This is my TC, which is already given. This is my TD, which was also already given. And this is my TA, which I can solve by solving the equilibrium equation and doing TB, I can solve for TA. Now, if I start drawing, my TB is 645 negative, right? So it goes 645 negative, and there is no load in between. So it goes straight here. From here, there is a positive 800, right? So it has to go up by 800. So it goes to 800. So this is 645. That is 155 extra to make it 800. Then there is no torque acting here. So it goes straight. And then finally at D, there is a torque of 500 and that's negative. So it's going to come down 500. So 155 here. So 345 on this side. Then again, there is no torque. So it goes straight. And then there is a negative 345. So it goes up here and puts to 0. Okay. All right. I hope that's clear. Now, what about twist diagram? The twist diagram here, it is 0. Here it is going to be 0. Now this is negative. So negative means, let's say it's clockwise. So the twist is also going to be clockwise. Okay. But then it's going to be positive. Therefore, the twist is going to change from clockwise to anti-clockwise, and it will slowly change. And somewhere it will go to 0 and then go up here. And then it has to come down to 0. So it will come down to 0. The change in angle, if you see, the change in angle here is due to there is a load acting at this portion, this load. Again, here there is a change in angle here, and that change in angle is due to this load acting there. Okay, so this change in angle is due to the clockwise load, that is anti-clockwise load that is acting here, and this change in angle is due to the clockwise load that is acting there. All right, so you have to draw this. Okay, and here are the free body diagrams to calculate the internal loads or internal torques. I hope that was understood. I will stop for a minute and wait for. Am I not recording it? Yeah, I'm. So what is the next problem? Next problem is easy. It's there in your assignment, I suppose. So there are two tubes here. One is a solid tube, which we call it as bar one, and then solid rod, and then there is a tube, hollow tube, which is we call it a tube two. So one is bar, one is tube. The bar is solid and the tube is a hollow, right? They're attached with each other by an end plate, and end plate is very fixed in the sense you don't assume any deformation in the end plate. Okay. So if I take a section, it's going to look something like this. This is my tube and that's my solid core inside. Okay, and the diameters are given D1 and D2. Okay, outer diameters. All right. Now, if I apply a torque here, I have been asked what should be your twist. Right. So if I apply a torque here, how the torque will be distributed? The torque will be distributed. Some of the torque will be taken up by bar one, and some torque will be taken up by the tube. I don't know how much. They won't be equal because their areas are not equal. So this is T1 plus T2 is going to be your total torque. So T1 is in bar 1 and T2 is in the tube 2. So it's going to be your total torque has been absorbed by both T members. Okay. Right. Now what I know is I can draw free body diagram. So I will free this section out or free the plate. If I free the plate, then I have to put a torque T1 acting on bar 1 and a torque T2 acting on the tube. Right? Because I have assumed they are T1 and T2. I don't know how to solve T1 and T2 right now. I don't know the values of T1 and T2, but I know they are something T1 and T2, and the T on T2 totals up to T. And I have only one equation, only the moment equation. So I don't have the second equation, and therefore I cannot solve this. And this is a statically indeterminate problem. To solve it, I need another completability equation. Now, what is that completability equation? How do I get that? So if I look at this picture, this is a very nice picture. And if I see at this portion, it is fixed, right? And no deformation is allowed in the plate. Therefore, if the plate rotates by an angle theta, both of these things will rotate by that angle theta, right? So both of them at any cross section will have same twist. Here is the diagram for you. So both of them will have same twist. Okay, because the fixed plate at the end is not deforming, so that's fixed. So that makes sure that everything rotates by same amount. Okay. All right. So phi 1, that is the twist of tube bar 1, and phi 2, that is the twist of tube, should be equal. So phi 1 should be equal to phi 2. That's my compatibility equation now, the deformation based equation. And I know phi 1 is going to be T1 L by G1 IP1, and phi 2 is going to be T2 L by G2 IP2. Right. So you can now solve it. It's going to be solved like this. Remember that in solving Excel problems, I told you this is the rigidity and divided by the total rigidity. Again, this is the rigidity divided by the total rigidity. Therefore, the load sharing happens based on how much rigidity it has. Okay, torsional rigidity. Load
Hello,
sharing in
sir.
Excel member happens based on how much, 1 minute, load sharing happens in the Excel member because of how much is its ratio of axial rigidity sharing. Remember if that formula that A1 E1 divided by A1 E1 plus A2 E2. Here also you see that G1 I1 divided by G1 I1 plus G2 I2. Okay, so the sharing of the torque is happening based on the ratio of their rigidity with respect to the total rigidity. Okay, so that becomes very important for you to solve problems when I have 3-4 bar members are together. Then you can tell, okay, I can do it. For example, if I put another rod here, how are you going to solve it? Are you going to go through all? You know this formula now, right? So you will just add up with G3 I3, G3 I3, and the third one T3 is going to be G3 I3 by total GI II, right? So you can do it that way. That's going to give you easy solution instead of going through all the problems. Right. So you had some question.
So in this figure, left figure, the T1 and T2 direction are wrong, right?
Wrong in the sense?
It should be left because in the upward case it was right. So T1 plus T2 has to be T. So left equal to right. That's the question.
Left equal to right. I mean,
Same
it
force
also depends which
moment
direction you are
equilibrium.
looking from. So you mean
So
that T1 plus
anyway, I
T2
mean,
is not equal to T?
uh,
Uh, Do you want to say T1 plus T2 not equal to T?
no, it is that T1 plus T2 has to be T, but the direction is wrong in the figure.
Hmm.
That's,
Here is this direction, this one is wrong.
yes,
This one is wrong or this one is wrong? Which one?
No,
You tell me double
both
arrow
are
is wrong or single arrow is wrong?
double arrow. Double arrow.
Why do you say that's wrong?
Curl is okay, means both are wrong. That's the doubt.
No, if you look
Sir,
from this side, is it wrong?
sir, just one thing. Sir, I think
This
I
is going
understand
to
his
be
question,
this way.
sir.
Yes, carry on.
So I think he's trying to say that as T is acting in the forward direction, to balance T, he's saying T1 and T2 will be acting in the opposite direction, sir. But that is not the case actually. That's what he's trying to
Oh,
say, I guess,
that
sir.
way. Okay. Oh, okay, understood now. Sorry, I did not understand before. Yeah, you are right that T1, T2 has to act in opposite direction to make sure that it balances T. Yes, you are right. Yeah, so we will do that.
Yes,
If you
same
wanted to
question.
do it, we will do it. So yes.
So
Thanks.
curl has to
I did
be,
not
means
understand
single
before.
arrow has to be, yeah, okay.
Right? So this has to go. Okay?
Both act on different bodies.
Now I suppose it's okay. Hello?
Sir, I mean, T.
Yeah,
Sir,
now I think it's Ankit. You have something to say?
sir,
Sir,
actually that was his question, sir. But I'm saying it's wrong, sir, because for plate B, because of the torque T, sir, and yeah, torque T, there will be an opposite torque at the end of the plate, sir, which will which will give a internal torque which is acting in the forward direction on the bar, sir. Right? Because this is anyways trying to pull it, no, sir. Like it's trying to pull the bar,
Not
sir.
pull
Pull
it,
the bar. I mean, like rotate in the
rotate it.
top. Yeah, yes, sir. So the bar also took in the same direction. So basically, like the end of the
No,
plate will
bar
have
will
this
rotate
direction.
in the bar will rotate according to the end plate load. That means it will rotate along this direction only. But
Yes, sir.
what he says that internal force will be generated in the opposite direction. Okay, that's what he said. But if the internal force generates in the opposite direction, no, I think it's correct. The directions are correct. Okay, the directions are correct. They're not wrong. Yeah, as Ankit has said, see, even if you take the plate out, okay, so the plate will have one is this side, other side will be this side, right? And therefore the bars will have a load on this direction.
Oh, okay, sir, got it, sir. Means
And
I
therefore
didn't
the bar
consider
will
the plate.
rotate. Okay, so the bar will therefore rotate along the direction of the external twist. Yes, thanks, Ankit. All right. All right. Okay, so that's how you solve this. But the objective of giving this kind of problems is they are both solved either with flexibility method or stiffness method. You have to go and understand which method I've solved, and you have to solve with the other method to make yourself comfortable. And the point I was trying to mention is the load sharing happens based on the rigidity share that they have. So that's very important to know, right? And that gives you an easy check as well as easy solutions when you have many problems together, many of the members together. Here are a few steps that are told how to solve this kind of problem. So please go through them. And there is This one I told in the last class that you have to, you have to remember these formulas. There is no other way here. You have to remember those formulas for square section, for an equilateral triangle, and for an ellipse. Okay, and yeah, so you have to remember them. And if there is a problem given on this part, you have to solve. A problem can be of this way, that there is a torque T given on the member, and this is a square section. What will be its tau max? So tau max will be T by C1 AB square, where A and B you have to find from the formula, and C1, C2 will come from a table. So don't worry about the values will be given. Only thing is you have to remember the formula. Okay. Other than that, there is no issue with this kind of problems. Okay, so with that, I'll stop.